Let's start from the servo gripper solution. Johannes already told you about our plug-and-play standard components that are basically very plug-and-play grippers in the sense that they come with a single M8 standard connector that can be of either 3 or all pins. In the case of the standard 3 pins, we have 2 of them used to provide power supply to the gripper, the 24 volts and ground. And another pin is used to command the gripper very easily because it's a digital output from the command control unit that can drive the gripper fully opening or fully closing motion. So it's just like an electro valve-like command, very simple to use. The command can be of either PNP or NPN type on the basis of the ordering code, but it's pretty easy because you just install the gripper, you plug the connector, and you are ready to go. This is very useful in some context, but sometimes it's not very compliant because sometimes customers need more and more flexibility in terms of controllability of the object, especially when the application requires these characteristics, or whenever the customer would like to get the most from our device. So in that case, we are pushed to create a more flexible interface that has the benefit that one can freely control the actuator, but of course there are some cons, like for example the commission that is getting worse somehow because you need to pay attention how to connect the gripper, and you must be a more expert user. And you need the external electronic that in our standard plug-and-play grippers is already embedded inside. But in the case of servo gripper, you need an external control unit. And to this purpose, we are designing right now a new group, a new family of electric grippers that we call them servo because the user has to connect an external drive controller to drive the servo motor inside. We call them MPLF. The final F stands for flat motors because all the grippers embed rotative brushless flat motor. And we made this choice because we can get higher power in a smaller dimension. We have on the top left picture an overview on how this new family looks like, and on the top right area we see a summary table that summarizes the main characteristic of these devices in terms of full stroke, total gripping force, and dimensions. I brought with me here a very first prototype in scale 1:1 that has been designed with our new technology, the 3D printer you saw yesterday downstairs. And this gives you an idea of how big is this component. So it's very good. We always try to make new products as compact as possible. And I think we did it also in this case because as far as I know, there are not so much compact device with this characteristic in terms of stroke and total force available at the jaws. The bottom side of this slide shows you the electrical connection, how the user should connect to this device to make them work. In the left part we see LF16 and 25, which is our smallest and medium size, and on the right part we see the biggest size 32. Concentrated on the smallest and the medium one, both of them come with one M12 12 pins connector. We have just one standard connector, very widespread in the industry, that brings up all the connection to the motor phases. So you can see here the first 6 connectors, 3 of them are for the motor phases and 3 of them are for the standard pulse sensors. And the last 12 and the last 6 pins are used to connect the feedback signal. That is a standard ABZ incremental encoder. Channel A, channel B, channel Z, and the 2 power supply connections. The And BLF32 comes with two M8 8-pins connector. We made this decision because we must keep in that case the transversal dimension as compact as possible, thinking also to the external cable and connector required to commission and to make this gripper work. And so here I put in two tables. The one on the left shows the connection to the motor with the M letter that indicates the motor connection and the E letter that indicates the encoder connection. And both these two letters are labeled and printed out at the frontal cover of the gripper, so the user cannot make any mistake during the installation. Or at least we try to reduce them the most possible. And even in this case, we choose to generate an incremental encoder signal because it's the most widespread on the market and quite easy to access and to control by means of standard drives on the market. What matters here is that we are not forced to adopt a specific brand of drive. They are open. So a generic user can use whatever drive he or she is used to use. Johannes showed you a few minutes ago, we developed for Winsor Robotics a special design of our plug-and-play electric gripper for the medical context and GMP application. Even if we are still in the design stage of our servo grippers, we have been already asked to create a similar solution for servo actuators. And we came out with this design that basically takes advantage of the same technology we used for the insole. So we recently designed a new silicone cover. I have a prototype here. I can let you watch directly. And this silicone material is a special one used for medical application because it can be cleaned with ultraviolet rays or hydrogen peroxide that are very common procedures in medical context. Here we see an overview of the product. In this case realized not only for the size of 32, but theoretically it can be scaled also for the smallest and medium size. The silicone cover is only one component of a set. We have here the silicone cover, the gripper, a mechanical interface that allows us to create a full, very easy to install device that can be customized depending on the final application. And we see here a first render where the cover material protects not only the gripper but a full set of components. We see two connectors coming out, one for the motor, one for the encoder, that go directly to an embedded drive. In this case, embedded in terms of the whole system, but it's the external with respect to the gripper. In this case, we selected a maximum drive, but as I told you before, it can be wherever you want. And one benefit of this kind of solution is that they usually want to have position control feature, velocity control feature, current control feature, and sometimes a mix of them, can freely do it by simply connecting to an external drive, who is already familiar to use. Furthermore, the drive provides some more functionalities, because since you can't rely on a bigger electric board, let me say, it provides connectivity. Most of them can be connected with standard feed buses, like an open Profibus or Ethercat, providing a real-time, fast deploying application. From a general perspective of manufacturing or production process, grippers, just like sensor devices, and in some cases even wall machines, are the simplest objects we can find inside an industry context. And they are components that take place here at the device level of a general representation of a pyramid, a structural pyramid of the industry. This picture here shows an example taken from the OPC Foundation of a pyramid at the time of Industry 4.0. So basically our grippers are here at the device level where sensor, actuators and machine are located, and they communicate one to each other, and they also exchange data with the above levels. Some data, most of them, I should say, are necessary to control the gripper of the devices. So they are directly connected with machine controllers, PLC or control units in general, that take place here at the control level. Some data available at the control level must be for sure be available at the control room of the general plant. So some of them might migrate from here up to here where the MES level is located. That stands for manufacturing and distribution system. Either in case the industry is made of one single plant or more than one, data should be available at the highest level, which is the ERP, where our overall monitoring system is available, and data here are available to the management, and management use them to make business and optimize the whole system. So we see here in this pyramid that one common information is the data transfer. That can be on the same level, but also can be between several levels. Nowadays, the communication at the highest levels is made by using Ethernet. Different types, but always Ethernet cables has physical layers. But when you are talking about low levels of this pyramid, we are moving toward field bus, because we need a real time. We need to exchange data very quickly and precisely between control units and devices. But historically, sensor and devices just come with very simple interfaces. Usually, as we saw in our plug-and-play grippers, an ACE connector with few pins, just power supplies and common signals. Or sensor come with the same interface, just providing information on the status of the sensor. Or generate a different signal that can be analog, for example, in the range 0 to 10 volts, 420 milliamperes, -10 volts. So they surely provide some information on the basis of their status, but they lack of a lot of data about their internal status, possible warnings, or predictive maintenance information. Since almost 10 years, I think, IO-Link has become the standard communication protocol at the lowest level of the pyramid, allowing to exchange more and more data among the devices like our grippers or sensors in general. Here we have a representation on how an IO-Link system looks like. We have at the very bottom level actuators and sensor. Here I put our grippers. And all of them behave like slave modules, because the IO-Link is based on a master and slave structure. All of them behave like a slave module, and they transmit, according to the IO-Link protocol that is depicted here with the orange lines, information to special units, special IO-Link units that are the master ones inside the networks. Masters unit, of course, communicate with some high-level devices by means of the green lines here that are typically field buses communication. The same concept has also reported here, where we see a comparison between a standard communication and the IO-Link enhanced communication. The main difference is that in the first case, very poor devices can only exchange on-off signals or nothing more in general. And with the IO-Link, we can establish a real bidirectional communication, so getting the most from the device in terms of data with status, possible alarms, and make some predictive maintenance sometimes. That is one of the key features of the IO-Link communication. As a sake of completeness, I put here an image showing a standard IO-Link connection, because besides 3 wires, are in general more than enough. Typically, IO-Link connectors, there might be M5, M8, or even M12 connectors, come with 4 or even 5 pins. 2 of them are for the power supply, the other one is for the digital communication. IO-Link is a push-pull 0-24 volt communication, digital bus, but you can switch a general IO-Link device to work as a standard device with simply on-off signal to be compliant with traditional interfaces. The other 2 pins, one is usually vendor specific, the other one is used to provide more power when devices need to have. Okay, when we first got to know the IO-Link technology, we suddenly start to think how to embed this technology in our product. And we had to face some issues, like the overall dimensional constraint, how to put the dedicated IO-Link technology inside our gripper. And the other important topic is to create a cost-effective final product that could be successfully used and widespread inside the industry. So instead of embedding directly the IO-Link technology inside our grippers, we decided to create an external component, especially because our MPPM 1606, that is the smallest plug-and-play gripper we have, it's really compact. We don't have space inside to add other components. And so we created the IO box, excuse me. The IO box. The IO box is a special IO-Link device that behaves like a gateway. That means it translates the IO-Link communication protocol available from the external world to a vendor specific, and ours in this case, so a proprietary communication protocol with a special version of standard plug-and-play grippers. What do I mean with special version? Well, they actually are standard pick-and-place grippers, but they share a digital communication interface to the external world. So using this IO box, you have here a very first overview, a render of the prototype, but I also have a physical mock-up. You can have a look directly, just to have an idea of what the dimensions are. The IO box presents 2 M12 connectors, one on the left, one on the right side. The connector on the left is used to connect this box directly to an IO-Link master unit, making this device the real IO-Link slave module. The other M12 connector is used to create a network of Gimatic standard plug-and-play grippers. So this picture here shows exactly what we would have in the future. So we have our IO-Link box and a series of connections of a proprietary bus, creating this group of connections by means of junction components and a terminal node. But what matters here is that cables are not special cables. It's just a 4-conductor scheduled cable freely available on the market. In this way, we can use one single IO-Link device to create a series of IO-Link functionally working devices. And we can just use one IO-Link port on the master IO-Link side, optimizing the whole system. Furthermore, if we, for example, get damaged this device for whatever happened during the working operation, we can simply replace this device without affecting the more, we say, technology advanced and, of course, expensive components that are our grippers. So, in this case, there is another advantage. We have a unique design we can focus on during this development stage. Several grippers can be connected to the same IO box in a bus-like architecture. We see here standard MPPM, but we can also connect MPLM, MPTM, 3 self-centering grippers, the radial ones, and so on. So theoretically, there is no limitation on what we can do, starting from our standard portfolio, which is already quite rich in terms of general portfolio on the market. And of course, the IO-Link interface in this case is very compact. We have only one board you can place wherever you want inside your cabinet and just take away a cable to connect the standard series of grippers. The IO-Link protocol requires that the master unit understands and knows who is talking to in terms of slave devices. So any device manufacturer has to distribute along with the product a specific file for the device that is called IODD, that stands for IO-Link Device Description File. This is just a text file, XML based as format, with a series of lines describing the identification of the component, so its name, serial number, and so on. And it also exposes information like the list of variables of the device and their addressing inside the memory space of the device. The problem of the IO-Link technology, from our point of view, is that it standardizes the protocol, so the language spoken by all the devices, but it does not standardize an information model. So my gripper could understand what a gripper from another brand is saying, but they can share different data, and the data structure can be different from one vendor to another. So information transmitted on the IO-Link cable are vendor specific. This generates one common issue. The manufacturer has to figure out which data are more of interest to get out from the device. So when we started the design, we try to ask our customer, please tell me what you really need. But when you ask a similar question to a customer, the typical answer is, well, give me everything that would be available. And this is understandable, but this is not really helpful in the design stage. So what happened, and it's not only for us, but for every main actor on the market, is that any manufacturer is trying to get the most from the device, guessing some functionalities, or trying to put information on the basis of some queries to the customer, some surveys, or the experience he or she may have from the past. So, process data and synchronous data, air parameters, which is typically are asynchronous, are vendor specific. Here, what I'm showing is what we are going to do for our grippers. We are going, as Gimatic specific data, to provide this following process data and this following parameters. Process data that are basically real-time data exchanged continuously between the devices, the slave devices and the master unit, can be split into input data for the gripper or output data for the gripper. So what we will provide are actuator commands, opening, closing, breaking, do some other stuff. We discuss with our customer and you can standardize some limited operation our standard plug-and-play gripper with IO-Link interface can do. We can set a force reference value, gripping force limitation, so creating the soft touch we already talked about, and limiting the gripping force accordingly with the specific data we share along with the IO-Link interface. As output data from the gripper, we can know the status of the actuator, if it is fully open, fully closed, the way in between, if the gripper has been, if the object has been gripped, if the device is in some error state, and similar information. And we can also get the position of the jaw. Remember that we are still talking about plug-and-play grippers, so these are not really servo grippers. We cannot really control them. But because of the IO-Link interface, we can query where the jaws are at the end of the motion, and we can indirectly know the dimension of the gripped object, for example, and so make a selection somehow. And in terms of parameters, of course, we will have identification information like the gripper code, batch, serial number, hardware, and firmware, software, and so on. We can set the performance or read out the expected performances of the gripper, like the maximum force, maximum frequency of the specific unit. Because, as I told you yesterday, when we saw how we test our plug-and-play grippers. We saw that every product is tested one by one at the end of the production line. We print out a declaration of conformity, and right now this is the most that we can do. But in the near future, we can put this information inside the gripper and let the user have them directly with the IO-Link functionalities.